All right, so let's say you have a scene, 3D scene with a light, and you want to check the light visibility, right? To see where the shadows are, and maybe store that into a texture, a light map that you can then render. Or let's say you have an enemy, and you want to check if it can see the player, line of sight check. Those are two examples of the many cases where you want to use raycast. What's a raycast? It's basically just collision detection between a segment and a 3D shape, like the 3D environment. And in this video, I want to talk about the way I solved this problem for my game engine, the algorithm I came up with. I'm not under the disillusion that I'm the first one to think about this algorithm. Probably exists somewhere, just haven't found it. If you know what it's called and you know the original algorithm, tell me in the comment and I add it to the description down below. But yeah, I just want to show that, show a little pseudocode, and let's get started. But before we get into the actual algorithm, just want to speak a bit on our representation for 3D shapes, right? Because there are actually many different ways of representing 3D shapes. Some that you know about, for example, triangle mesh, right? Where you have a list of vertices, a list of indices, which make up a mesh. Triangle mesh, they allow you to represent any 3D shape, as long as the shape doesn't have infinite faces like a circle, but for the purposes of video games, basically any 3D shape can be represented with triangle mesh. Usually when we want to do collision detection, we don't really use triangle meshes. We don't really use arbitrary shapes. We rather use convex shapes. There are many reasons for that. But basically, it's really easy to detect collisions between convex shapes, really hard between non-convex shapes. So for the purposes of this, we'll check collision detection between a line segment and a convex shape, which we can also call a convex hull, right? Okay, and how do we represent our convex shape? There are basically two main ways. The first one is by simply a list of vertices, and we define the points that are inside the shape are the points that are a linear convex combination of all the vertices, so basically the points that are in between all those vertices. That's a useful representation. We use it, for example, for the GJK collision detection algorithm between convex shapes. For the purposes of raycasting, though, it's not really applicable. At least I haven't found a way to use that representation to detect collision detection in an efficient manner between a line segment and the shape. So for our raycasting, we rather use the other representation, which is a planar representation. Basically, each face is a plane, and we have a list of delimiting planes, and we define the shape as the set of points that are behind every plane, right? So behind every faces. For example, this is a plane, this is the space that is outside in front of the plane, and this is the space that is behind the plane. And those points in there that I have shaded in gray are the points that are behind every plane, right? That's a pretty common definition for a convex shape. So our shape is defined by the planes. And just to point out quickly a little refresher about analytical geometry, this is something you've probably seen in high school, but as you know, the equation for a plane is ax plus by plus cz equal d. Maybe you used to say ax plus by plus cz plus d equals 0. I prefer to have the d on the right side and then pass it off and have the minus right here. But that's down to preferences. I just think it's more explicit if the d is on the right side. But either way, this is the equation. If you write it in vector form, it's n dot x minus d equals 0, because here you can see it's just a dot product with the normal vector and the point xyz, right? So the normal vector is the vector with components a, b, and c, and you do a dot product with the point xyz, and this gives you this term, and it's equal to d. I pass d on the other side. So this is the equation for a point on the plane, And conversely, this is the equation for a point behind the plane or on the plane. So it's just a less than or equal right here. And this is the equation for a point in front of the plane. It's greater than here. So basically, the n dot x minus d is the distance, the signed distance of a point to the plane, right? Right here, I've written it. The signed distance from a point to the plane is n dot x minus d. So if a point is right here, the signed distance will be that part right here. That's n dot x minus d. And if the point is right here, it will be n dot x minus d, and this will be negative, right? Okay, so that's pretty basic. With that out of the way, I think I can start talking about the actual algorithm. All right. So this is our setup. We want to check the collision between the line segment from A to B and the shape, which here I've drawn as 4 faces. I will be doing all the drawing in 2D, of course, but it's the same in 3D. The formula for the plane generalizes since I've written it with the dot product. And so it's basically the same in 3D. I just drawn it in 2D because my artistic skills aren't that good. All right, so the algorithm, basically, as we saw, the points are in the shape if they are behind every plane of the shape, right? Conversely, if we invert the condition, we have that the points are outside the shape if they are in front of any of the plane of the shape, right? So basically, we want to check if there exists a point on the line segment that is inside of the shape. Or if you prefer, we want to check if every point on the line segment are outside the shape. If it's the case, then there's no collision. If it's not the case, then there is a point inside the shape and there is collision. What we're going to do is we're going to clip the line segment iteratively with each plane until we can confidently say that the entirety of the line segment is outside the shape. So we are going to clip the line segment and keep only the part that may still be inside the shape. There will be 4 cases for that. So let me do an example. We'll iterate over every plane and we'll see every cases. So let's start with this plane right here. So in this case, you have that A is in front of the plane and B is behind the plane. In that case, of course, this is the part of the line that you want to keep is the part that is behind the plane, because that's the part that could still be inside the shape. That part right here, you're certain it's not inside the shape, you're certain it's outside the shape, since it's in front of the plane, right? So you compute the midpoint, the point of intersection between the line and the plane, and you set A to that point. So now our new A is there. As you can see, the only part of the segment that we study right now is the part that is behind the plane. That part now we don't care, since we have changed the A. Our new segment is the shorter segment right here. Next plane right here, you have the case where A is behind the plane and B is behind the plane as well. In that case, we do nothing. Because you see, if we want to clip the line segment to only keep the part that is behind the plane, then in that case, the entirety of the line segment is behind the plane, so we have nothing else to do. Third case is if that in the plane, if B is in front of the plane and A is behind the plane, right? In that case, we'll once again compute the point of intersection and set our new B to that. This time we replace B. That way we only keep the part of the segment that is behind the plane, right? Because the part that is in front, we are certain is outside the shape. And this is our last case, it's actually our exit case, is when A and B, both A and B are in front of the plane. In that case, we are certain that the segment is outside the plane, outside the shape, sorry. Because of course, we only keep the part of the segment that could still be inside the shape, and we see that the entirety of that segment is outside the shape. So in that case, the algorithm returns false because it's outside the shape. So there's no collision, right? So those are the basic four cases. A is in front of the plane, B is in front of the plane, A and B are in front of the plane, and not A nor B are in front of the plane. That's the four cases. Okay, let's take a look at the pseudocode for that algorithm. It's pretty simple, but this is the pretty simple version. I have another version that I will show you later, which is more optimized and which is better because you can parallelize it. But let me not get too ahead of myself. Let's take a look at that one. So this is the simple method. We iterate over every convex hull, right? And so every shape that are composing our world. We set A to the first point, B to the second point. Then we iterate over every plane of the hull, right? We compute distance A using dot A and the plane normal minus plane dot D, right? So that's the equation we saw earlier. Once again, B dot N minus D for the distance to B. Then if both A and B are behind, we continue to the next plane. If A and B are both in front, we skip to the next hull. There is no collision with this hull at least. So skip to the next hull, in code this would look like a goto, right? Goto and skip right here. If you're in a language that doesn't have a goto, then I don't know, factor out the method. But you see, skip to the next hull means do not return and get to the next hull, right? Do not return true, get to the next hull. M is the midpoint. I haven't written the method because in the next version of the algorithm, we actually won't need it. We won't need this method because since we don't need this method, I haven't written it down, but it's pretty basic. You can find it on the internet, line to plane intersection, right? If A is in front, we replace A with the midpoint. Else it means that it is B that is in front, and we replace B with the midpoint. And once we've done that, and we haven't skipped any time, once we've iterated over every plane, right, and we haven't skipped at any point, it means that we still have a line segment AB that wasn't in front of any plane entirely, right? So there is a collision. So we return true. And if we've iterated over every hull and at no point was there a collision, we can simply return false. So this algorithm is already pretty decent, but I want to show you the new version I found when I started to try and parallelize this algorithm. So basically implement it with SIMD intrinsics to kind of try to get a speed up because it was a bit too slow for my use case. And I found out a better version of this algorithm, which reposes actually on pretty much the same idea. And I show you that one, okay? So let's take our same example as earlier. This is the same shape as we had earlier, except this time we want to keep the A and B constant. We don't want to change the A and B at any point, right? And instead of computing the midpoint, we want to just compute the scalar value of that midpoint along the line. So let's say that 0 is A and 1 is B, and in between it's 0.5, here it's 0.25, here is 0.75. That's basically the value of a point in the linear coordinates of the line AB, right? Of the segment AB. So imagine if we had a vector basis, which is AB, which is a one-dimensional vector space, right? 0 would be the coordinate of A, 1 would be the coordinate of B, and in between 0 and 1, there will be 0.5, etc. And for every plane, like we did earlier, we're going to compute the midpoint. If A is in front of the plane, we say that the midpoint is a quote-unquote lower bound. If B is in front of the plane, we say that the midpoint is an upper bound. Here, A is in front of the plane as well, and B is behind. So this is a lower bound again. And for this plane, both A and B are behind, so like we did earlier, we won't do anything, okay? So we have computed 3 coordinates which are either lower bound or an upper bound, right? And the idea of this algorithm is simply that the lower bound indicates, like we did earlier, the lower bound indicates the lower part of the segment that could still be inside the shape, right? So for example, behind this segment right here, behind this lower bound, this could not be inside the shape because it's in front of the plane, right? Behind this lower bound, this could not be inside the shape because it's in front of the plane. In front of this upper bound, so behind this upper bound, so up there, right? This could not be inside the shape, right? Because this part could not be inside the shape because B is in front of the plane. And we want to see if we take the highest lower bound, so basically the lowest point where you could still be inside the shape, and the lowest upper bound, so basically the highest point where you could still be inside the shape, we want to check if those are greater or smaller, right? So in that case, the lower bound is higher than the upper bound, which means that if you want to be inside the shape, you need to be smaller than 0.67, sorry, and you want to be higher than 0.82. There's no such thing as that, right? So basically the check, once we have computed every lower bound and every upper bound, the check is simply to say if the maximum lower bound is greater than the minimum upper bound, then there is no collision. Okay? Does that make sense? All right. So that's the idea, basically. We want to compute every lower bound and every upper bound, take the maximum lower bound and take the minimum upper bound and compare them. You can see that this reposes on the same basic idea as the earlier algorithm, but you'll see why it's much better actually. Once we write the pseudocode, we'll see why it's much faster. Okay, but before we check out the pseudocode, I just want to point out, how do we find the value of the bound? How do you find the value of the intersection between the line and the plane? Let me recenter that. Okay, right. How do you find the value between the value of the intersection between the line and the plane? So like we said, A is 0, B is 1. Basically the formula is distance minus the distance of A over the distance of B minus the distance of A. How does that work? Put simply, the distance of A is that, right? The distance of B is that. So minus the distance of A is you start at 0, and minus the distance of A is from here to there, this is the distance of A, right? This vector right here. Minus the distance of A is from here to there, that way, right? So this is minus the distance of A. You go from 0 to there, it's indeed the midpoint. And then you divide it, you scale it down by the distance between A and B, which is distance of B minus distance of A. That's the delta distance, basically, final minus initial distance, right? So you scale down that distance by that distance, and this indeed gives you a distance scaled down between 0 and 1, right? So that's the equation for finding the coordinate of the midpoint, right? Let's check out the pseudocode, right? That's the pseudocode right here. You'll see it's basically the same thing as earlier, except this time we have, instead of resetting A and B, and instead of modifying A and B, we have a L, which is lower bound, and U, which is upper bound, right? We compute the thing like earlier. We compute the value of the current bound, so the intersection. and if A is in front of the plane, we set lower bound. If A is in front of the plane, this is the lower bound, right? And in that case, since we want to find the maximum lower bound, we'll set the lower bound as whatever is the max between the current lower bound and the new lower bound we've just computed. Else, it means that B is in front of the plane and that this is an upper bound. And since we want to find the minimum upper bound, we'll set U to whatever is the minimum between the current upper bound and the new upper bound we've just computed. And at the end, we have a lower bound and an upper bound. And if the lower bound is greater than the upper bound, like we said earlier, in that case, we return true. Is that a mistake? Let me think about this. Maybe I have just made a mistake. No, that's wrong. Lower bound is smaller than the upper bound. In that case, you return true. Sorry about that. Okay. So why is this algorithm so much better than the earlier one? Then for one, you don't have to compute the midpoint of the plane. You just have to compute the midpoint in terms of the coordinate system between A and B, right? So that's a bit faster than computing the intersection between a line and a plane, but marginally so. It's not that much faster. The true reason why this algorithm is much faster is because since we're not changing A and B, there is no longer a loop carried over dependency, right? What does that mean? It means that each loop iteration does not depend on the value of the last iteration, right? Each loop iteration could be computed individually. There is no dependency between one iteration and the last one. And what that means is that if you want to parallelize this method, meaning compute it all at the same time, you can do that. Because you can essentially compute any iteration of this loop without worrying about the result of the earlier one, since we are no longer changing A and B over the course of the algorithm. So basically, you can implement this with SIMD, for example, which allows you to check 8 planes at a time per iteration, 8. So that's 8 times faster. And you compute with SIMD the distance of A, the distance of B, the value of M, etc. You compute with SIMD or as well the mask of where is it greater, where is it smaller, right? And once you've got that, the last thing you want to do is simply compute the max and the mean. With SIMD, it's very fast as well. It's just a few instructions. And basically, you do the entirety of the loop in just one iteration with SIMD with 8 planes at a time. This makes this version of the algorithm compared to the last one, basically 6 to 8 times faster. In theory, since SIMD can do 8 operations at a time, it should be 8 times faster. But in actuality, most shapes don't have 8 planes, they are rather 6 planes, you know. And so in that case, we compute 6 planes at a time, not 8 planes at a time. So we actually have a 6-time improvement. And from my profiling, I show you on screen the SIMD version of this algorithm, and you'll see it's actually pretty crazy. It's not that complex, right? And it's actually a 6x improvement, so that's pretty great. And yeah, so that's basically the final version of the algorithm I've managed to do. If you see something you could improve with this algorithm, please tell me in the comment. I would love to read that. If you think that my algorithm is actually dumb and there is a better one somewhere on the internet and you have a better idea, please tell me. I'll gladly read that. And yeah, that's basically everything I had to say. Do I have anything? No, thank you for watching. Like, comment, etc. And I'll see you in the next one. Bye bye.